Hello, my name is Caleb, and I took part in the Emertxe online internship, and we built an EV ADAS dashboard. So I'm here to walk you through it and show you a demo on what I built. So the EV ADAS dashboard is a solution to a problem, and it contains real-time speed, SOT, and range monitoring. Because sometimes not all dashboards can incorporate this into one dashboard, but the solution was to incorporate all of them into one ADAS dashboard. So it also contains ADAS collision and blind spot detection. It measures the temperature and also alerts for faults. And all of this data was streamed over over UART to Python. And it also has a tiered alarm system, which range from advisory to critical, and various drive mode control for eco, normal, and sport. The project requirements were to model real EV dynamics such as torque, speed, SOC, range, etc., using the STM32 Blue Pill, and also to implement ADAS, which also took care of forward collision warnings for blind spot detection and the measuring time to collision using ultrasonic sensors. So I was also detected and managed faults such as the motor overheating temperature, low SOC, and critical collision. And all this was streamed live over UART to a real-time Python dashboard. And so the tools and development environment. So for the firmware and coding of the STM32, we use the STM32 Cube IDE. For simulation, hardware simulation, we use PixMLab. Also for the programming, especially for GPIO, ADC, the timer, and UART peripheral drivers, we use the STM32 HAL library. For the dashboard and telemetry processing, Python and its various libraries were used. A VSP was used to create virtual port pairs for serial communication, and PySerial was used for UART serial communication with the MCU. So the system architecture was quite simple. We used sensors simulated, of course, using potentiometers to measure them. So for the acceleration and brake pedals, potentiometers were used in place of them to simulate them, and the data gotten from these potentiometers and various other sensors such as ultrasonic sensors was fed to the blue pill, which contained the EV control and the ADAS engine. And then all this was streamed over UART to a Python dashboard, which displayed a speedometer, the SOC bar, and the ADAS bed view. Also, 3 timers were used: timer 1, 2, and 3. And so, real industry, just a few. Instead of the ECU or vehicle control unit, we use the STM32 Blue Pill for the simulation. And instead of actual sensors and proximity sensors, we use potentiometers to simulate it. Instead of CAN or line bus, we use UART. And instead of a multi-tone buzzer alarm system, I use the tiered alarm from non-advisory to warning and critical. So there were 4 main states, which are the parked, ready, driving, and regeneration. And if there was any error or any fault, it would immediately jump into the fault states. So the models included motor torque, which is the physics model, regenerative braking, the power draw of the battery across time, the SOC and range, and the thermal model to measure the motor temperature. So the ADAS engine also consisted of 3 main things, which was the forward collision warning. It measured the distance between the car in front and also estimated if there was going to be a collision, then the time to collision, and also used ultrasonic sensors to measure blind spots, such as to detect if there are any cars in the blind spots. So for the fault detection and safety, the faults included measuring motor temperature, which was denoted by fault OT, low battery, basically, which was denoted by fault SOC, and critical collision warnings for fault collision. So the alarms range from alarm none, where normal operation, alarm advisory when there was a blind spot detected, alarm warning if there was a probability of a collision, and alarm critical if there was a very high probability of collision or it even already happened. So the EV telemetry frame fed data directly into the Python dashboard, and it fed speed, SOC, torque, temperature, range, acceleration, and brake. So the UART command shell was also built such that commands could be sent back to the STM32 to enable certain commands. So the Python dashboard has a speedometer, a battery SOC bar. It also shows speed history, EV metrics panel to show the torque, acceleration, brake, and temperature. And also consists of an ADAS bird's eye view, such that it would be easier to actually see your blind spots and how your car is actually in real life. So I learned a lot. I learned more on embedded C and about the STM32 HAL library. I also learned more on ADC, on UARTs, on more on sensors and certain physics models, sensor signal processing, safety state machines, also live data visualization using Matplotlib and Python, and serial protocol design through UARTs and other sense, how to communicate from one port to another. So the results were quite interesting. And so now I'm going to show you the live demo. So we first started, okay, let's talk about how. So we first started by setting up the main microprocessor, the microcontroller. Use the STM32, use the STM32 cube ID to annotate the pins, what each pin is meant for, and its role. And then the programming happened in STM32 cube ID, where if I'm to expand here, you can see all the header files were placed in the include folder, and then the main files, the C files, were placed in the src folder. So we will not go through the whole code, but this is the folder structure, and these are the code which make sure that everything is working properly. And yes, so then for simulating the ports, we used VSP, and I used COM7 and COM6 to communicate. And then we come to PixMLab, which we use for the simulation. So, come in. Sorry, let me just get this. So continuing the demonstration, we have PixMLab, which was used for the hardware simulation. So for the sensors, we use potentiometers to simulate the acceleration, brake, SOC, and motor temperature. And we use the ultrasonic sensor for the front, left, and right. The left and right were mainly for the blind spot detection, and these are the alarm indicators. So this is for the collision, front collision, the blind spot left, blind spot right, and this is for faults. So if, for example, there's a high motor temperature, this will come on, and if it's low, there's no fault. So if there's a blind spot, okay, it is a bit slow sometimes. So if yes, so the blind spot detection comes on, left blind spot, when the distance between the car and its blind spot is very low. Same for the right, as you can see, and for the forward, if you are to reduce it, yes. So this is Victim Lab, and then we come into Python dashboard. So I used VS Code. So let's run it quickly. Okay, that took a long time, but here we have it. So this is our Python dashboard. So as you can see, we have the speedometer, the speed, which display the speed, and then there's the SOC bar, which displays the state of charge remaining. Then this is the ADAS bird eye view, so you can see the car in front is at a distance, and you can also see the time to collision, the speed of the vehicle, and then the EV metrics such as torque, acceleration, brake, motor temperature, all here. And this is the speed history. So if you are to, and this is all being read over UART through COM7. So if you are to increase the values here, and also maybe just create a warning. Let's just create warnings, alarms. So if we are to do that, see it is responding. It is responding as various alarms. So you can see the fault, the alarm is critical, the collision and everything to be flashing red. You can see the left blind spot is also very slow. So this is the EV ADAS dashboard, and yes, this is the code for the Python dashboard. We will not go through it, but this is the code. So I guess that's all. And yes, thank you for watching.